Good. Good afternoon, everyone. I know that I'm the only thing that separates you from the coffee break, and it's difficult to compete against the snacks, but I'll try to do my best. Very well, let's get started. I guess I shall introduce myself first. I am Llorenc Escola Farras, PhD in Amsterdam, University of Amsterdam and QSoft. And this is a joint work together with Florian Spielmann, which is titled Single-Qubit Loss-Tolerant Quantum Position Verification Protocol, Secure Against Entangled Attackers. I know the title is long, but I'm going to go through all of it. And please find there like the QR that brings you to the link of the archived version of the paper. Okay, what is position verification? I think that the term itself is a bit self-explanatory. So you have a map, and you want to verify the location of something or someone. Okay, let's zoom in the map. For instance, myself, I would be here in Maryland, and I will play the role of a prover. And I want to prove my location. I want to show that I'm actually here to two people that do not trust me for whatever reason. These two people could be, for instance, on the one hand, my promoter in Amsterdam, that is going to play the role of a verifier. And on the other hand, in Hawaii, probably having a better time, my supervisor that is going to play the role of a verifier as well. And they both are going to challenge me. So they are going to send me a challenge. I'm going to specify later on the type of the challenge, and I have to respond to them. And if I answer correctly, they're going to accept my location as good one. Okay, so how does it work? First, I'm going to start with the classical, and then I'm going to go to the quantum. So the most general setup for a classical position verification for one dimension is the following. So you have an arrow that is going to determine the position. And here at position P, that's going to be me. I'm going to be in there. And then I'm going to have two verifiers, V0 on my right and on my left, that are going to challenge me. OK, so the time arrow goes down. And consider the light cone of V0. And also consider the light cone of D1. So they're going to send messages, both X and Y, classical messages at the speed of light, so that they intersect for the very first time at position P. So now I get the two challenges, and I have to compute like something. Let's call it f of X and Y. And then I have to also, in my light cone, I have to respond on time. If both answers A are correct and arrive on time, check. The verifiers accept my location as good one. And all of this is based on the fact that this thing, that I took it from Star Wars, so speeding faster than the speed of light, it's forbidden by the laws of physics. Very well. But there's a universal attack that is trivial for this setup. Consider the following. And here is where I'm going to introduce our beloved friends, Alice and Bob. So instead of myself being at position P, assume that Alice is here and Bob is there, and I'm not in the middle. So they do the following. So they are going to cover my shoulders, and they are going to pretend that I am at the position P that I claim to be. So they intercept the classical messages X and Y. They make a copy. This is important. Make a copy, broadcast one part, and keep one part from themselves. Bob does the same. And here, they both have enough information to compute the challenge. And they have enough time to send it to the closest verifiers. So for the point of view of the verifiers, they got the correct answers on the correct time. So both A are correct and arrive on time, and therefore the verifiers are fooled. Okay, but in the quantum realm, there's the no-cloning theorem. I think that you all are familiar with it, but I made a nice slide, so I want to show it. So assume we have a machine. Of course, the machine is quantum. That's why I put an atom there. And you put a dolly ship. And I think that, Anne, you mentioned a couple of days ago that why do we have a ship as like the icon of QCrypt? And I think that it must be because of that. So we put, turtles. No. First dolly ship. But of course, quantum. You put it inside of the machine and plop, you make two copies. That is forbidden by quantum physics. So that you cannot do. Okay, so let's add the magic word in position verification. Let's put it quantum, a Q. And remember, as long as we can prove that quantum is better, we don't lose our jobs. So here, instead of sending classical message, you send a quantum state also from the other side, and maybe you have to answer with quantum things as well from the point of view of the prover. And remember, this prevents the attack that I explained before, because such a machine that copies row 0 and row 1 doesn't exist. Okay, let's make it more concrete. And I guess that lots of you are already familiar with the BB84 QKD protocol. And based on these ideas, I'm going to show you a quantum position verification protocol. So assume the following setup: test verifier 0, that is going to pick at random one BB84 state, either 0, 1, plus, or minus. And the verifier is going to send it to the prover, and from the other side, the prover is going to receive in which basis he or she has to measure. The prover measures the qubit that he received in the basis that he also received and broadcasts the outcome. So attacks, because this can be attacked, right? I'm going to show you how. So this, I forgot it was originally introduced by these people, Ken, Munro, and Spillen in 2011. So assume that they pre-share an EPR pair like this. Alice intercepts the qubit. She makes the teleportation measurement. She broadcasts the outcome. Bob just measures the local register in basis X that he just intercepted. And of course, 0 is as usual computational basis, X is as usual, 1 is as usual Halmar basis. So, and here they have enough information to just recover what the prover would do in the middle. Okay, but what if we restrict attackers and they do not pre-share any entanglement? So then they can at most succeed breaking the protocol with a probability of roughly 0.85. Okay, that gives some hope. Let's study security under certain constraints. But I have to say that there's a big no-go theorem that says that all quantum position verification protocols can be attacked. But on the good side of that, the best known general attack requires an exponential amount of pre-shared entanglement, which it's like in efficient terms, it's not practical. So our ultimate goal is to find an easy protocol which is very difficult to attack. And also, we shouldn't forget the experimental implementations, because there are some problems in the experimental implementations that are big enough that they force us to redesign our protocols. So when you send photons, you can think of sending photons through an optical fiber, like this. What's the first problem? That there is loss. Another problem, that the quantum information travels slow. So picture by the snake here. And if I said at the beginning that everything was based on sending messages at the speed of light, this is a problem. And also, if you have a quantum network with like optical fibers connecting nodes and stuff, it's likely that this is not going to be in a straight line between 2 points. At the end, you will have to do a longer path. And that we also have to take into account. Okay, first, how can you take advantage of photon loss? Assume that Alice intercepts a qubit, measures in a basis that she guesses, broadcasts all the information, and here, when Bob sends the basis that she had to measure, they both know if she was right in her guess. If so, answer the outcome that you got in the measurement. Otherwise, say, okay, the photon was lost, and with this perpendicular symbol. Moreover, taking advantage of slow quantum information, what if we have the following scenario? So here, Alice just takes the qubit, sends it to Bob, because always we assume that attackers have superpowers like faster fibers, better measurements, and better devices and everything. So sends it to Bob, Bob measures in the correct basis, and just broadcasts the outcome, and then they can answer to the verifiers and fool them. Okay, just to wrap up these 3 things that I mentioned, the 3 major problems that quantum position verification faces are the following. Instead of Bermuda, because that I'm going to introduce the Bermuda triangle of quantum position verification. So instead of Bermuda, we're going to have photon loss. Instead of Puerto Rico, we're going to have slow quantum information. And instead of Florida, we're going to have entanglement. The 3 problems that I told you about before. First, there are protocols that are fully loss tolerant. So photon loss is not a problem in those protocols. But what about entanglement and slow quantum information? So we have protocols that are reasonably secure, well, secure against reasonable amount of pre-shared entanglement. But we also have protocols that are resistant against slow quantum information, and we even have both things simultaneously. But what happens when we face the 3 problems all together? There's like a dangerous area. So we try to say planes, but boom, they explode. Okay, so let's analyze this area inside and what happens in there. So first step, we analyze the loss. Remember the previous protocol where one BB84 state is sent and in which basis you have to measure is also sent from the other side. And we analyze this parameter, eta, which is the transmission rate from V0 to P. Okay? And we also have to look at this. This is like a simulation of the photon being lost in here. Okay, and now we have to answer, to add another valid answer, which is going to be photon loss, because the honest party sometimes is going to say, okay, I lost the photon, I didn't receive it. Okay, and we are also going to introduce an error, because like the prover is going to be subject to some error, and this error can come either from the measurement device that is not like very precise whatsoever, or also like you send a 0 and through the channel from V0 to P, it gets flipped to a 1. Okay, so actually the number of correct answers that we expect is eta times, the number of times that you receive the photon, 1 minus the probability of being wrong, of the error probability. Okay, let's study security against unentangled attackers. And our goal is to upper bound the attacker's probability of answering correctly. So the most general thing that they can do if they do not pre-share entanglement is Alice intercepts the qubit, couples to some local registers, some ancilas that she has, some whatever she might have, and sends one part to Bob and keeps a part for herself. And Bob, without loss of generality, just broadcasts X, because any quantum thing that Bob could do, Alice could also do. And then let's go here. So they share at the time that they have to answer a quantum state rho. And the most general thing that they can do is to perform a POBM to this state that they share. So, and they answer either 0, 1, or the photon was lost, and same for Bob. And at this time, they have both to answer to the closest verifier. And here it comes our first result. The best probability that they can attack the protocol given a transmission rate eta is given by the following expression, which is like pretty nice, I'd say. It's cosine squared pi over 8 times eta plus sine squared pi over 8 times 1 minus eta. And this holds for the range of eta between 1/2 and 1, because remember that I said that if eta is less than 1/2, you can just guess the basis, and you can perfectly break the protocol. Okay? The techniques to prove this, I think are very interesting, because we could also find applications to some other cryptographic primitives. And I can talk about it later in the questions if you ask about it. But here, to wrap it up a bit, the first result in experimental parameters, we can show the following. So if you have a transmission rate eta and a probability of error given by this, if you are in this region, the protocol is secure and otherwise is attackable. Okay, so if you are an experimentalist and you want to implement that in a lab, you just go here, you look, and we have a tight characterization of the security for this protocol. But I did not forget that it is still insecure if attackers pre-share a single EPR pair. So step 2, use step 1 to fix it. Okay, so consider the protocol that I've been talking about all this time. And now, instead of sending classical information from one side saying, okay, you measure in the computational or Hadamard basis, what you do is the following. You send 2-bit strings of length n, and sending classical information is easy. It's almost for free. And then you measure in a basis given by a Boolean function, either computational or Hadamard basis. So this extension was proven to be secure if attackers pre-share entanglement, a certain amount that is linear in the n, and n is the length of the classical information, and arbitrarily slow quantum information, which is also something good. And here, like what we did, it was to introduce the loss, the lossy parameter, which is eta. And using the previous result that I showed you before, like that graph with the blue and gray areas, that leads to some technical lemma. And then if we combine this with the techniques of the other people, we can show our main result, which is the following. If you have a number of pre-shared qubits, which is linear in n, so entangled attackers, plus slow quantum information that can be arbitrarily slow, plus photon loss, the protocol is still secure. And this, to put it like in a graph like before, we could find some area that the protocol is secure. We also have some area where the protocol is attackable, and those results are not tied, so there's an area that we don't know what happens in there. But the important thing is that it is possible to perform it securely. So the blue region here. Okay, so what does it mean? This means the following. If we compare the protocol with the attackers, the protocol, and if you have loss, requires a classical information of 2n for both the honest parties and the attackers. But the amount of qubits that you have to manipulate as a honest party is 1, whereas if you are an attacker, it's linear in n. So to make it like in numbers, if you send a kilobyte of information, you just need to manipulate a single qubit, whereas the attackers need to manipulate 4,000 entangled qubits at least. We believe that this is exponential, but we don't have a proof of that. So it means that this is easy to handle for the honest parties, but it's complicated for the attackers. Okay, so what we did, I'm going to be back to the Bermuda Triangle of photon loss, of quantum position verification. So we brought this bar, and we pushed it to half of it, because for a photon loss greater than a half, you have an attack, and now you can send planes in there. But that's not enough, right? Because there's some area that we still want to cover. And spoiler, we don't cover it all, but we push the bar a bit more. So instead of sending the information, the quantum information, in two bases, like the computational and Hadamard bases, that this you have security for eta greater or equal than a half, you use more bases. And we introduce the third dimension. And then if you go to the blogosphere, you send states I and minus I, the eigenvalues of the Y Pauli matrix. And then you have more security for photon loss. So eta greater or equal than a third. And the more bases you put, we computed the results, and we had more security. So if you have 5 bases in which you encode the quantum information, you have security for eta greater or equal than a fifth. So what does it mean? That if we go to the Bermuda Triangle, we could push it to 1/3 of photon loss, or 1/5 of transmission rates, and now we can send more planes over this forbidden area. And with that, I would conclude, and thank you for your attention.
Thank you, Llorenc. We have time for some questions.
Hi, thank you for your, over here.
Where? Okay.
Yeah, thank you for your phenomenal talk. If you go back to the last slide, if you continue to add additional bases, can you discuss, I guess the one before that.
Like this?
Yeah. In the limit, as you keep adding more and more bases, where does the eta, does it scale almost arbitrarily close to 0, or can you comment on that?
For that, we need to solve some semi-definite programs. And for that, we need to solve them in a computer. So we solve them for some examples. And the trend is like I put 10 bases, and we had security for eta 1/10. So it seems that it's going to that direction, but we don't have an analytical proof for that. And we just give the way that, okay, so you want to put n bases, so you have to solve the problem. I mean, we just show, okay, solve this SDP, and then you get the results. But the SDP grows quite a lot with the number of bases that you put. It becomes bigger and bigger.
Thank you.
Question on the same thing. So the more bases you add, though, does that significantly decrease your rate? Because now the probability of measuring in the incorrect basis is higher?
And then you have more error.
Okay.
Because the closer they are, the more error you're going to make when you measure with your device.
Right. So there's probably some optimization to be done. We're like,
I guess so.
Yeah.
Yeah.
Okay.
Yeah.
Interesting.
And now we are going, because there's a follow-up work with that we're trying to get rid of this thing. So luckily, or I think that we don't need to do that anymore, because we know how to get rid of that. But it's something that is going to be posted soon. Thank you.
Actually, I have a question.
Sure.
So there's, I guess, one other way of addressing this Bermuda Triangle is there's this work on, at the cost of computational assumptions, making it the communication classical, which addresses like photon loss and quantum communication
between who?
Between the verifiers and the prover.
Everything classical.
Well, the prover is still quantum.
But then you need at least one quantum communication, right?
No. This is the beating classical impossibility opposition.
Oh yeah, but then you need quantum computers.
Yes. You still need the quantum computers, but you solve the problem of photon loss and slow speed. But at the same time, it comes at the cost of entanglement.
Yeah.
So I was wondering, so I guess it still doesn't resolve it completely. And I was wondering, what do you think is, do you have insight on which direction is maybe more promising?
I think it's like to implement it currently. This is more promising in the sense that you just need to measure 1 qubit. And with the other one, you need to have a whole quantum computer. And of course, you get rid of like photon loss and stuff, but you need like a quantum computer everywhere where you want to to do the to perform the protocol. And I think that it has pros and cons, of course, because here we're still like struggling with photon loss. But at the end, the honest party just needs to measure 1 qubit.
Thank you very much. Let's thank all the speakers for the session again.